At the edge of sleep, where silence grows, where distant stars in crimson glow, a secret pulses through the sky, a planet breathes, but no one knows why. Not barren rock, not raging flame, but oceans deep without a name. A whisper carried through the black, a pulse of life. The cosmos calls back. Across 120 light-years wide, where hydrogen clouds and dark tides hide, a distant world sings through spectral streams, its chemistry dancing with biological dreams. James Webb has seen what none had guessed, a biosphere beyond, where life may rest. The silence is broken, the void has replied, proof of life, where once it was denied. So close your eyes, let your thoughts ignite. We'll drift through galaxies, through endless night. Hit subscribe. Return when your mind craves flight. Tonight, we voyage through wonder and light. Prepare for revelation. Prepare for dreams. We begin. In the stillness of a December morning, when most of the world turned in its familiar rhythm, a quiet tremor rippled through the halls of human knowledge. It began not with an explosion or a grand unveiling, but with the soft, rhythmic blinking of data points on a computer screen. Deep within Cambridge University, in a modest room packed with processors and wires, Niku Medusan stared at the incoming stream from the James Webb Space Telescope, a river of ancient light captured from 120 light-years away. Each photon that arrived had journeyed through the endless abyss, brushed past comets, weaved through star systems, and finally landed upon humanity's greatest machine, Webb, stationed 1,000,000 miles from Earth in the perpetual cold of Lagrange Point 2. These photons were survivors of interstellar passage, carrying within their delicate vibrations a story too subtle for the naked eye, too distant for human senses. Yet here they were, being sifted and translated into colors, curves, and numbers. Medusan watched as the graphs stabilized, a pulse steady and unmistakable. Hidden in the symphony of infrared wavelengths was a signature, a sharp dip, a faint glow, a spectral fingerprint that should not have existed in the emptiness of space. It was dimethyl sulfide, a compound so rare and peculiar that on Earth it comes only from life, from the breath of phytoplankton, the sigh of ocean microbes, the metabolism of living cells. His heart pounded. He was witnessing what generations of astronomers had dreamed about and doubted in equal measure. Not a vague hint, not an ambiguous reading, but a molecular announcement from another world. Dimethyl sulfide was there, strong and undeniable, reverberating in the light filtered through the atmosphere of a distant planet. The room seemed to contract around him, the world outside forgotten. As his mind expanded into the cosmos, he was knee. No longer a scientist confined by walls and gravity, he was a witness to history unfolding, to the first true murmurings of life beyond Earth. The implications bore down on him like gravity, overwhelming and exhilarating. But this was no solitary moment. Across the globe, observatories, satellites, and laboratories buzzed in synchronized wonder. The scientific community is a tapestry of cautious thinkers trained to doubt, to question, to demand rigorous proof before belief. Yet here, buried in the pristine data of Webb, was something defying skepticism. Not just a chemical, but a calling card of biology. What made this signal more astounding was its statistical strength. In the vast realms of astronomical uncertainty, where every discovery is tempered by probabilities and error bars, the confidence in this detection stood tall at 99.7%. A 3 sigma certainty, the threshold where coincidence collapses and reality takes shape. The margin for error was smaller than the chances of flipping a coin and landing heads 1,000 times in a row. This was not noise, not artifact, but a voice across the stars. Outside the sterile comfort of observatories, the world continued unaware. People commuted, cities pulsed with routine, the moon drifted over sleeping towns. But within the minds of a few, the universe had just shifted. For the first time, humanity stared at a world that breathed, a world that whispered back through the void. The telescope that had delivered this revelation was itself a marvel. Webb, the golden-eyed sentinel of the cosmos, gliding in the silent dark, its delicate mirrors unfolding like petals to capture the faintest glow from the oldest and most distant corners of the universe. It had been designed to look back in time, to the fiery birth of galaxies and the coalescence of stars, but in doing so, it had stumbled upon a revelation far more personal, the echo of life familiar yet foreign. The discovery was centered around a planet designated K218b, a name cold and clinical, a mere catalogue entry among thousands. Yet in that moment, it transformed from a number into a beacon. Scientists had known of K218b's existence for some time, glimpsed indirectly by the way its bulk tugged on its parent star. But now, its identity bloomed into clarity. It was not just a rock adrift in space, but a potential cradle of life, an oasis in the stellar desert. The signals told a tantalizing story. The planet lay in the constellation Leo, orbiting a red dwarf star named K218, a star much cooler and smaller than our Sun, yet steady and enduring, fusing hydrogen in its core with slow determination. Around this humble star, K218b danced in a perfect rhythm, its path bringing it into Webb's view at precise intervals, allowing the telescope to peer through its atmosphere during each transit. Each pass revealed more than just light. It peeled back the secrets of the planet's gaseous veil. First came the soft signature of water vapor, then the breath of methane, the exhale of carbon dioxide. But it was the unmistakable presence of dimethyl sulfide that broke the silence of the universe, a signal of life as we understand it, pulsing in the atmosphere of a world far removed from Earth's nurturing warmth. Yet, with each discovery, new questions formed like clouds on the horizon. What kind of life could thrive in an atmosphere dominated by hydrogen? What forms would evolution take under a red sun's dim light? Would these organisms possess senses, cognition, perhaps even civilizations beyond our comprehension? Or were they simple, robust life forms, vast colonies of microscopic beings shaping their planet's atmosphere in ways we were only beginning to grasp? The atmosphere itself was a paradox, a thick, hydrogen-rich shroud creating conditions utterly alien to Earth, yet fostering temperatures. Yours ideal for liquid water, for stability, for life to flourish. Unlike the capriciousness of our planet's climate, K218b offered a constancy, a serenity governed by gravitational balance and atmospheric chemistry. Medusan leaned back, overwhelmed by the momentousness of the discovery. Across the oceans, other scientists were validating, recalculating and cross-checking, but deep down the truth was already evident. The universe had spoken, not in grand explosions or cosmic cataclysms, but in the gentle, quiet fingerprint of life carried in light. The implications stretched beyond science. It touched on philosophy, on our ancient yearning for connection, on the stories humans have told themselves since the dawn of consciousness. No longer could we claim to be alone, the singular expression of biology in a lifeless expanse. Somewhere, beneath a sky tinged in crimson and swirling clouds of hydrogen, life existed, utterly indifferent to our gaze, yet connected to us through the shared miracle of existence. As the data continued to stream, the world unknowingly inched toward a new era. The moment would not be marked by parades or fireworks, but by the quiet dawning realization that life was no longer the domain of Earth alone. It was a feature of the cosmos. In that December morning, as the stars blinked above and the Earth rotated below, a threshold had been crossed. Humanity, for the first time, was no longer just looking at the stars. We were listening, and they had begun to answer. There is a peculiar magic in light. It slips through the fingers of the cosmos without sound, without resistance, carrying secrets of unimaginable age and distance. In this quiet stream, time itself becomes pliable. To look into the sky is not merely to witness a present world, but to stare backwards, into the depths of the past, into moments sealed away by the relentless expansion of space. A light in its elegant simplicity serves as both a messenger and a mirror, revealing not only where we are, but where we come from, and, perhaps most profoundly, what surrounds us. The light that Niku Medusan watched on his screen, deciphered from its quantum whispers into solid data, had left the atmosphere of K218b 120 years before. When those photons departed their alien world, humanity was just beginning to carve its presence onto the fabric of Earth. Cities were powered by coal and steam, the hum of internal combustion was only a murmur of the future, and the world remained vast and unexplored. In the time it took that light to traverse the interstellar gulf, empires had risen and fallen, wars had scarred continents, and humanity had ventured beyond the atmosphere for the very first time. That same light now told a story that stretched even further, of chemical dances beneath alien clouds, of molecules forming and breaking, of life exhaling and sculpting an atmosphere we could barely imagine. Light was no longer a passive reflection, it became a dynamic dialogue between distant worlds. The magic of Webb's discovery lies in this principle of absorption. Light filtered through a planet's atmosphere before reaching us. As the planet crossed in front of its star, a tiny fraction of the starlight seeped through its gaseous shell, and in this thin veil, secrets were imprinted. Certain wavelengths were absorbed by specific molecules, methane, carbon dioxide, water vapor, and each left their own telltale fingerprints on the spectrum. What reached Webb was not pure starlight, but a distorted echo shaped and molded by the presence of alien chemistry. It is easy to forget the delicacy of this process. Imagine standing on a hill on Earth trying to detect the flavor of a single drop of water evaporating in a distant ocean by measuring how sunlight changes as it passes through the mist. Now extend that challenge across light years through the blinding glare of a host star that burns billions of times brighter than its orbiting planet, T. The fact that humanity could extract any information from this subtle light signature was staggering. Yet here it was, data beyond doubt, revealing dimethyl sulfide with remarkable clarity. Through this mechanism, Webb transformed from a telescope into something more intimate, a cosmic mirror that reflected not just distant worlds, but their essence, their breath, their living processes. Every blip in the data, every notch in the wavelength spoke volumes about atmospheric composition, planetary climate, and, above all, biological potential. Yet light, for all its gifts, also withholds. It teases us with partial truths, veiled glimpses, silhouettes painted in infrared hues. While we could sense the presence of life-signifying molecules, the true architects remained hidden. What forms had evolved under K218b's thick atmosphere? Were there vibrant oceans teeming with microscopic life, or vast mats of algae-like organisms glistening beneath alien skies? Did creatures crawl along the shores of distant continents, leaving ephemeral trails washed away by hydrogen-rich tides? These were visions we could not yet access, stories waiting beyond the reach of current instruments. Still, the light offered more than chemical signatures. It granted us knowledge of the world's thermal complexion. By analyzing the infrared spectrum, Webb measured the average temperature of K218b, revealing a surface warmed to 120 degrees Fahrenheit. A number so perfect, so elegantly balanced, it felt less like coincidence and more like an invitation. Too cold, and life's delicate chemical engines stall. Too hot, and the scaffolding of organic molecules crumbles into entropy. But here, in this narrow corridor of warmth, complexity could thrive. K218b's place in its solar system, orbiting a dim red dwarf star, initially seemed unpromising. Red dwarfs, after all, are known for their stellar tantrums, violent. Flares and radiation bursts capable of stripping atmospheres bare. Yet K218b endured its thick atmosphere, acting as both a shield and a blanket, softening radiation's bite while cradling the world in thermal stability. Light, therefore, was not just illumination, it was survival. Filtered through layers of hydrogen, refracted and softened, starlight nurtured life in conditions radically unlike those on Earth. Through the lens of Webb, we were not just peering at a single world. We were unlocking a method, a technique by which the universe could be surveyed for life without ever stepping foot beyond our star system. Transmission spectroscopy, as scientists called it, became the philosopher's stone of modern astronomy, a tool capable of transmuting light into knowledge, darkness into revelation. It was this method that opened the gates to countless other worlds, Already, Webb had begun scanning other promising candidates, each orbiting stars dimmer than the sun but offering warmth and stability through gravitational proximity and atmospheric protection. The dream of cataloguing life-bearing worlds moved from distant fantasy to the threshold of modern science. In the coming years, we would not just know of Earth-like planets, we would read their atmospheric compositions like ancient scrolls, deciphering tales of climate, weather, and life cycles. But the mirror held even deeper implications. Light crossing such distances became a time capsule, a messenger from the past. The K218b we observed was a snapshot from over a century ago. What might that world look like now? Had life advanced, retreated, or perhaps even birthed intelligence capable of gazing back toward our own star? Every photon received was history, every spectral line a memory. To study distant light was to weave ourselves into a cosmic narrative far grander than any single civilization, far older than any known history. This realization stirred a deeper humility within the scientific community. We were not simply explorers, we were late arrivals to a party billions of years in the making. Planets like K218b had existed long before human eyes learned to seek the stars. Life may have danced beneath alien oceans while humanity's ancestors still huddled in caves, fearing the thunder. The cosmos waited for no species. It evolved, it thrived, and it perished beyond our awareness. Only now, with instruments like Webb, could we catch faint echoes of this eternal drama. The distant mirror taught us something sacred. The universe is not silent. It hums with the quiet breath of living worlds, sending fragments of itself across light years in a language written by molecules and wavelengths. Every star we observe is more than a furnace of nuclear fire. It is a lighthouse illuminating hidden realms, some barren, others vibrant, many beyond imagination. In those photons streaming to Earth, we found ourselves, our thirst for understanding, our need for connection, our place in a vast, mysterious cosmos. Light was no longer a passive force. It became our bridge, our translator, our gentle guide through the celestial wilderness. As the data continued to unfold, scientists felt the weight of a new responsibility. For every glimpse we took of distant skies, distant eyes might gaze back. For every atmosphere we analyzed, another species might one day analyze ours. The mirror does not reflect in one direction. It links observer and observed in a silent, ancient communion. Thus, through light, through this distant mirror, humanity stepped into a broader existence. We were no longer confined by oceans or gravity. We were listeners and interpreters in a universe that had been speaking for eons. All we had to do was learn how to hear. Beyond the veil of Earth's atmosphere, where our pale blue world dissolves into the inky silence of space, there spins another world. It circles a quiet crimson star in the constellation of Leo, hidden far from our immediate cosmic neighborhood. A world named with simplicity, K218b, yet possessing a depth that defies comprehension. It is not just a rock adrift among the stars. It is a sanctuary, a crucible, a living theater where chemistry and time have conspired to produce conditions more gentle, more nurturing than anything we have known. From the first glimmers of data, K218b distinguished itself. In a universe filled with frozen deserts and searing infernos, it offered a rare and delicate balance. The planet orbits its red dwarf host star within a precise orbital range, what astronomers call the habitable zone, where temperatures flirt with the miraculous threshold that allows water to persist in its liquid form. And in this narrow, precious belt of orbital real estate, K218b performs its endless dance, shielded by an atmosphere more massive, more protective than Earth's. Yet to label K218b merely habitable is to undersell its mystery. It belongs to a strange and fascinating class known as super-Earths, worlds larger than our home planet, but smaller than the giant ice planets that linger on the outskirts of star systems. With a mass roughly 8.6 times that of Earth, K218b straddles a curious threshold, its nature long misunderstood by the scientific world. For decades, planets of this size were considered gas-enveloped behemoths, lacking solid ground and inhospitable to life. But with Webb's revelations, that old assumption crumbled like ancient stonework, giving way beneath the weight of discovery. K218b emerged not as a gaseous giant, but as a water world, an immense globe enrobed in oceans that put Earth's seas to shame. If our oceans are vast, covering 70% of our surface, K2818b's are titanic. Beneath the thick atmospheric blanket lies a global sea, potentially hundreds of miles deep. The pressures below are inconceivable, crushing by terrestrial standards. Yet within that watery expanse, life-supporting chemistry brews and bubbles, defying the simplistic models humanity once clung to. Scientists envisioned a surface unlike anything terrestrial observers had ever witnessed. No continents breaking the ocean's horizon, no mountain peaks piercing clouds. Instead, a seemingly endless sheet of water stretching from pole to pole, with waves cresting under a red-tinged sky, reflecting the dim warmth of a star far cooler and redder than our own. There would be no blue skies on K218b. The atmosphere, saturated with hydrogen and laced with exotic molecules, would bend the light into hues of amethyst and rose, painting a world that seemed forever trapped within a cosmic sunset. And within those skies, within those oceans, the chemistry of life whispered. The James Webb Space Telescope had detected signatures of water vapor lingering high in the atmosphere, and deeper within the spectral lines, more complex molecules waited to be unraveled. Methane, carbon dioxide, and most strikingly, dimethyl sulfide. It was as though the planet exhaled softly into the void, broadcasting the rhythms of biological processes to any who could listen. Yet for all its familiarity in chemical signatures, K218b was alien in scale and structure. Gravity pressed down more firmly than on Earth, threefold heavier. A person weighing 150 pounds on Earth would be pinned by over 400 pounds of force on K218b. Walking would be laborious. Movement would be an effort of will and muscle beyond what humans experience. Yet for native life forms, if they existed, this gravity would be home. It would sculpt their forms, dictate their evolution, perhaps fostering robust, squat life, built to thrive beneath constant pressure. The gravitational pull had other consequences, beneficial ones. It ensured that the atmosphere clung close, resisting the erosive forces of space weather, of stellar winds that had stripped away the atmospheres of countless worlds, including our neighboring planet Mars. While Mars gasped in a near vacuum, K218b's atmosphere stood proud and thick, embracing the world in a cocoon of warmth. The planet's proximity to its star raised further curiosities. Red dwarfs like K218 burn faintly compared to the Sun, releasing just a fraction of the light and heat. This necessitated K218b's closer orbit, closer than Mercury orbits the Sun. Yet thanks to its atmosphere and unique orbital dynamics, it avoided the searing fate of our innermost planet. Instead, it basked in a comfortable, stable warmth, maintained not by the star's raw energy, but by the efficiency of its own atmospheric insulation. Tidal locking was inevitable. K218b, like many close-orbiting worlds, kept one hemisphere forever turned towards its star, while the other remained in perpetual darkness. This phenomenon could have spelled doom, a world divided between scorching day and frozen night. But K218b defied that fate. Its thick hydrogen atmosphere redistributed heat across the globe, softening the extremes, ensuring that even the dark side remained warmed by the planetary blanket. Imagine standing at the twilight zone, where eternal day gives way to everlasting night. Above, strange constellations would glitter differently than on Earth. The sky would shimmer with auroras, painted not just by magnetism, but by the complex interplay of gases unknown on our world. Beneath your feet, the ground would be liquid, vast, eternal oceans swelling in slow, massive tides, stirred not by a moon, but by the gravitational embrace of its star. And beneath those waves, the true heart of K218b likely lay in the depths. Without landmass, east to stabilize climates, the oceans became the planet's pulse, regulating temperature, storing heat, nurturing life. On Earth, life began in such depths, in the warmth of hydrothermal vents, amidst mineral-rich plumes isolated from sunlight. Could the same be true for K218b? Could its oceans hide ecosystems of bioluminescent beings clustered around thermal upwellings, feeding on chemical gradients in a world where sunlight never penetrated? Speculation surged, but so did cautious optimism. K218b redefined what it meant to be habitable. It demonstrated that life's cradle need not be confined to Earth-like environments with nitrogen-rich atmospheres and continental surfaces. Life could thrive in hydrogen clouds, in deep alien oceans, under the red glow of a quiet star. Its very existence forced scientists to redraw the boundaries of the habitable zone, to question assumptions about what environments life could adapt to or even prefer. Perhaps K218b, with its stability, its infinite oceans, its shielded atmosphere, was not just habitable, it was ideal, more nurturing, more consistent than the dynamic, often violent Earth. As these revelations settled into human consciousness, K218b transformed in status. It was no longer merely a point on a star chart. It became a symbol of the living cosmos, a reminder that Earth was not unique in its ability to harbor life. And somewhere, in the gentle lap of hydrogen tides, life pulsed and thrived, indifferent to distant observers, yet connected through the shared language of molecules, of warmth, and of survival. K218b had always been there, quiet, patient, spinning through the ages, but now humanity had turned its eyes upon it, and in doing so discovered reflections of its own origins and possibilities. A world unimaginably distant, yet suddenly so close to the human heart. If Earth's atmosphere is a gentle whisper, K218b's is a deep, resonant hum, thick, vast, and heavy with the aroma of life. Above its endless oceans, far from any solid ground, hangs an atmospheric shroud so dense it bends the very color of the sky, shifting the familiar blues into mysterious shades of violet and crimson. It is an air rich with chemistry, pregnant with clues of biological processes, and, most astonishingly, imprinted with the fingerprints of life. What makes K218b's atmosphere extraordinary is not just its thickness, but its composition. Where Earth's skies dance with nitrogen and oxygen, this distant world breathes hydrogen. It envelops the planet in a vast cocoon, a lightweight gas by earthly standards, but present here in volumes enough to generate crushing atmospheric pressure at the surface and to trap heat with remarkable efficiency. This hydrogen-rich sky is more than a protective blanket. It is the crucible in which life appears to flourish. The James Webb Space Telescope's data revealed a rich cocktail of gases swirling within this alien air: methane, carbon dioxide, water vapor, and most captivating of all, dimethyl sulfide, a molecule that on Earth has only one known source: life. From oceanic microorganisms to marshland bacteria, dimethyl sulfide is crafted by living cells, a metabolic signature exhaled into the winds. To see it 120 light-years away was nothing short of revolutionary. It was as if K218b had sighed, and the echo of that breath traveled across the darkness to reach our waiting instruments. In human science, detecting a single molecule from such distances would normally be a footnote, a curiosity easily dismissed, but dimethyl sulfide carried with it a burden of meaning. Unlike methane or water vapor, which could emerge from volcanic eruptions or chemical interactions in the crust, dimethyl sulfide lacked a plausible geological or abiotic source. It pointed stubbornly toward biology, toward oceans teeming with life forms we could neither see nor imagine. And it was not alone. Accompanying this biological marker were curious concentrations of methane, levels far above what a sterile, lifeless world should sustain. On Earth, methane's lifespan in the atmosphere is short. It is quickly broken down by sunlight, oxidized and washed away. Its persistent presence on K218b suggested active replenishment. Something beneath the clouds was breathing out these gases faster than photochemical reactions could remove them. The atmosphere revealed not only life's possible existence, but life's dominance. It was an ecosystem large enough to reshape an entire world's chemical equilibrium, detectable across interstellar space. Scientists spoke in whispers about what this implied. Life on K218b was not eking out a marginal existence in isolated vents or rare niches. It was abundant, vigorous, planetary in scale. Yet with every answer came new questions, swirling like the winds that circled the globe. What kinds of organisms could survive in such an atmosphere? On Earth, life is oxygen-loving, dependent on nitrogen balance, evolved to thrive in relatively thin air. But K218b's thick hydrogen clouds suggested a fundamentally different biology. Perhaps life that did not breathe oxygen, that did not photosynthesize in the traditional sense, but fed instead on hydrogen gradients, metabolizing exotic molecules, flourishing in conditions that would poison earthly life in seconds. Speculation turned to Earth's extremophiles, organisms that defy traditional limits, bacteria that thrive in scalding hydrothermal vents, archaea that metabolize methane, microbes that survive crushing pressures and total darkness. If Earth's biosphere could generate such adaptability, what unimaginable forms might K218b's life have taken under its unique atmospheric chemistry? The possibilities stretched beyond our experience. Perhaps enormous plankton-like creatures drifted beneath the oceans, exhaling life signatures into the sky. Or vast mats of microbial colonies covered the ocean surface, photosynthesizing under the red glow of the star, crafting dimethyl sulfide as a metabolic byproduct. Some researchers proposed a biosphere dominated by chemotrophs, organisms feeding on chemical energy rather than light, turning the oceans into a factory of biological gases. The atmosphere's stability added more intrigue. Unlike the chaotic climates of other exoplanets, K218b's dense air redistributed heat with exquisite efficiency. Where Earth has seasons, storms, and unpredictable shifts, K218b's atmospheric circulation appeared to maintain a near-uniform temperature across its surface. The day side, forever facing the star, was tempered by reflective cloud layers and gentle convective currents. The night side, bathed in darkness, remained warm, its heat preserved by the atmospheric thickness and greenhouse trapping. Such a uniform climate eliminated many of the survival pressures found on Earth. Organisms on K218b might not need to migrate, hibernate, or endure long cycles of starvation and feast. Life could flourish continuously, unburdened by winter or drought, its energies channeled entirely into growth, reproduction, and evolution. This led some biologists to postulate that life there, unhampered by terrestrial stresses, could evolve complexity at unprecedented speeds. Even the air's pressure, crushing by earthly standards, likely played a nurturing role. Under higher atmospheric pressure, chemical reactions proceed differently. Gases dissolve more readily into liquids, potentially accelerating metabolic processes. Perhaps K208b's life forms operated with remarkable efficiency, thriving in a high-pressure chemistry lab spanning the entire planet. The role of light also differed. K218b orbited a red dwarf star, emitting a softer, longer wavelength light compared to the Sun. The planet's sky glowed with a muted reddish hue, offering a continuous twilight even on the day side. Photosynthetic organisms, if they existed, would have evolved to harvest this light efficiently, using pigments unknown to Earth science, perhaps reflecting back blues and purples, painting the oceans with surreal colors from above. And then there was the silence. No radio signals, no technological artifacts, no detectable signs of intelligence, just the quiet, unbroken presence of life's chemical rhythms. This provoked both humility and wonder among the scientific community. Not every world aspired to technological civilization. Not every form of life sought to alter its world beyond recognition. Perhaps on K218b, life remained harmonious, integrated into the planet's cycles, leaving no trace of tools, cities, or industry, only the unmistakable breath of biology on a global scale. 218b's living air, therefore, became a window into alternate evolutionary futures, what life could become when unshackled from the demands of intelligence or the march of technology. It reminded humanity that complexity, survival, and flourishing did not necessarily culminate in civilization, but could exist as a persistent hum beneath the clouds. To peer into K2N8b's atmosphere was to peer into a possible version of life itself. Life adapted not to Earth's narrow definitions, but to the vast possibilities of the universe. It revealed the versatility of biology, the adaptability of life, and the error of assuming our planet's blueprint as the only model for habitability. With each photon captured by Webb, each molecule detected in the distant air, humanity's view of the cosmos expanded. K218b was not an anomaly, it was a signpost. It suggested a galaxy where life might be the rule, not the exception. A universe where living air breathed softly across countless worlds, each unique, each adapting to its own cosmic rhyme. And in that realization, Earth itself felt both smaller and greater, a tiny world in an endless sea of planets, yet part of a vibrant living cosmos, sharing invisible threads with distant oceans, alien skies, and the timeless hum of life beyond the stars. Of all the variables that define life as we understand it, few are as crucial or as unforgiving as temperature. Life walks a narrow bridge, balanced precariously between the icy void where molecules freeze into silence and the searing heat where chemistry melts into chaos. On Earth, the thin sliver of temperate climate harbors the vibrant tapestry of life, while extremes of heat and cold remain the realm of only the hardiest organisms. And so, when the James Webb Space Telescope measured the atmospheric temperature of K218b, the numbers seemed almost implausible. An equilibrium so precise, so life-favoring, it challenged the very notion of cosmic coincidence. The readings spoke clearly. K218b, though swathed in dense clouds and orbiting a cool red dwarf star, maintained an average atmospheric temperature of approximately 120 degrees Fahrenheit, just shy of 50 degrees Celsius. To the human body, this is warmth that feels heavy, humid, and oppressive. But to biology, particularly to the foundational chemistry of life, it is a golden range where molecular reactions thrive, where enzymes catalyze efficiently, where cellular machinery hums along at optimal pace. It is, in a word, perfect. This revelation sent ripples through the scientific world. For a planet so far from Earth, with so many differences, gravity 3 times stronger, a hydrogen-rich atmosphere, an orbit locked in perpetual day and night, the surface conditions seemed oddly, almost eerily familiar. The climate on K2N8b was neither an inferno nor a frozen abyss. It was a sustained, stable warmth, ideal for liquid water, for metabolic activity, and for the slow, deliberate evolution of complexity. But how did such a perfect balance emerge? How could a world orbiting a faint red dwarf, receiving only a fraction of the energy Earth basks in, sustain such life-nurturing temperatures? The answer lay in the thick, heavy air above K2N8b's endless oceans. Its atmosphere acted as a colossal thermal regulator, capturing the meager energy from its star and trapping it beneath vast clouds of hydrogen and other greenhouse gases. This atmospheric greenhouse effect, far more potent than anything on Earth, ensured that every drop of warmth was conserved, every photon of stellar light recycled within the planetary envelope. Hydrogen, while the lightest element, served here as an insulator of extraordinary power. Unlike Earth's nitrogen-oxygen mix, K2N8b's hydrogen atmosphere was superbly effective at absorbing infrared radiation and preventing the escape of heat into space. This created a stable, self-regulating thermal blanket, one that eliminated the wild temperature swings common on other rocky worlds. On Earth, temperatures rise and fall with the turning of the day, the cycle of seasons, the whims of weather. But on K2N8b, the thick atmosphere smoothed away such chaos. Its heat remained steady, its climate persistent. Day and night, equator and pole, light and dark. The atmospheric circulation worked tirelessly to redistribute energy, maintaining an almost surreal uniformity across the globe. One might expect the perpetual day side of K2-18b to bake under constant exposure to its red dwarf star, while the night side froze in eternal darkness. Yet the Webb data suggested otherwise. Ocean currents, driven by the relentless push of wind and temperature gradients, moved heat around the planet. Atmospheric convection towers climbed from the equator to the poles, ferrying warmth into the shadows. Even in the absence of direct sunlight, the T-side remained relatively mild, shrouded in the planet's atmospheric embrace. For life, such a stable thermal environment was not merely comfortable, it was transformative. Terrestrial organisms endure cycles of feast and famine, of bloom and dieback, dictated by the turning seasons and the irregularity of climate. On K2-18b, life could, in theory, flourish continuously, unburdened by the constant struggle against environmental extremes. Energy could be invested not in survival, but in growth, in complexity, in advancement. In Earth's oceans, the most diverse and abundant ecosystems cluster in regions where temperatures remain stable. Coral reefs, tropical shallows, equatorial estuaries. Extrapolate that principle to K2-18b's global ocean, warmed gently beneath a perpetual atmospheric blanket, and the potential for life's abundance becomes staggering. Whole layers of biomass could proliferate in the upper reaches of the ocean, feeding on chemical gradients, basking in the muted light, flourishing without interruption. This stable temperature also enabled something else: chemical richness. Certain life-essential reactions, like the formation of complex carbon structures, require consistent thermal conditions to proceed efficiently. Organic molecules are fragile. Too cold and they crystallize into inactivity. Too hot and they break apart. But in the balmy waters of K2-18b, prebiotic chemistry could have unfolded unimpeded, assembling proteins, nucleic acids, membranes, and, eventually, life itself. For astrobiologists, K2-18b became more than a curiosity. It became a template for a new category of potentially life-supporting worlds, Hycean planets. Worlds enshrouded in hydrogen atmospheres, blanketed by global oceans, maintaining stable, elevated temperatures ideal for biology, even when orbiting dim, ancient stars. K2-18b, with its near-perfect thermal profile, stood as the prototype of this emerging class, rewriting the rules of planetary habitability. Critically, this new model expanded the search for life. No longer confined to Earth-like analogues with nitrogen skies and rocky continents, humanity's gaze shifted to distant water worlds orbiting common, long-lived red dwarfs. These stars, far more numerous than our Sun, burned slowly for tens to hundreds of billions of years, offering their planets stability and warmth long after the Sun has extinguished its nuclear fires. The implications were profound. While Earth and its solar siblings dance within the fleeting lifespan of a G-type star, K2-18b belonged to a lineage of worlds with the potential to host life for epochs, far longer than the history of human civilization, perhaps longer than the entire saga of life on Earth. If intelligence arose there, it would have the luxury of countless millennia to evolve, adapt, and endure. Yet the perfect temperature did not imply uniformity. Subtle variations, driven by ocean currents, atmospheric eddies, and tidal forces from the red dwarf, likely carved microclimates into the aquatic world. Beneath the surface, gradients of heat and pressure would create ecological niches, each fostering unique life forms, each contributing to the symphony of biological activity detected in the atmosphere. Perhaps, near the terminator line, the eternal twilight zone between day and night, upwellings of nutrients fed blooms of microscopic life, sending plumes of organic gases skyward. Perhaps in the depths of the ocean trenches, geothermal vents spewed minerals into the water, nurturing chemosynthetic ecosystems. The possibilities were infinite, constrained only by the laws of chemistry and the creativity of evolution. From our distant perch, all we could do was listen to the delicate balance of atmospheric molecules, to the thermal heartbeat of a faraway world. But through that listening, through the silent language of temperature and chem, a picture emerged, a world alive not in spite of its alien nature, but because of it. A world where life, cradled by perfect warmth, could rise, endure, and perhaps one day reach out across the stars to answer our call. For now, we listened in silence, humbled by the discovery, awed by the perfection of a temperature too precise to ignore. K218b was more than a point of data. It was a promise, a glimpse into the boundless adaptability of life in the universe. And with every analysis, every calculation, humanity took another quiet step toward answering the question that had lingered since our ancestors first looked skyward. Are we alone? On K218b, the warm winds whispered, and the answer drifted tantalizingly on the edge of certainty. Far beneath the weighty skies of K218b, where sunlight filters weakly through dense clouds of exotic gases, an ocean stirs, a sea unlike any on Earth. Its waters are not quite the transparent blue we know, nor are its tides driven by a familiar lunar rhythm. This ocean is deeper than imagination, wider than any earthly map can comprehend, and suffused with chemistry so strange it borders on the surreal. It is an ocean rich in hydrogen, an element that transforms the very rules of marine existence, and in its fathomless depths it may hold wonders and enigmas we have barely begun to fathom. To understand this alien ocean, we must first unshackle ourselves from Earth's comfortable norms. Our seas, covering most of our planet's surface, are driven by a balance of salinity, heat, and currents. They are habitats where light dances to considerable depths, where oxygen dissolves freely, and where the interaction of continents and atmospheric patterns create an ever-shifting dynamic surface. K218b offers a world without land, without shorelines to mark the limits of ocean's reach. Here, water stretches endlessly, interrupted only by the slow churn of planetary winds and the quiet pressure of gravity. Yet the true peculiarity lies within the very chemistry of the sea. Infused with hydrogen from the massive atmosphere above, K218b's ocean operates on different physical principles. Hydrogen, light and volatile, dissolves in great quantities into water under the crushing pressures present on such a world. This mixture of water and hydrogen creates a fluid environment that challenges earthly intuition, a liquid that is both less dense and more buoyant, where sound travels differently, where pressure gradients shape currents in unpredictable ways. The depths of K218b's ocean are monstrous in scale. On Earth, the Mariana Trench sinks a mere 11 kilometers beneath the surface, an awe-inspiring abyss by human standards. On K218b, estimates suggest oceans could extend hundreds of kilometers deep, plunging into realms of unimaginable pressure and temperature. Here, the hydrogen atmosphere presses down relentlessly, increasing the ocean's pressure exponentially with every descending meter. Such depth leads to phenomena absent from earthly seas. Deep within these crushing depths, the temperatures and pressures may align in such a way that water transforms not into gas or ice, but into a supercritical fluid. In this state, water behaves as both liquid and gas, erasing the boundaries between phases, creating a dense, exotic medium where chemical reactions may proceed rapidly, efficiently, and perhaps with surprising biological consequences. And then there are the diamonds. On K218b, carbon is abundant, present in atmospheric methane, in dissolved organic compounds, in potential biological byproducts. Under high pressure, carbon does what it always seeks to do: crystallize. On Earth, deep within our mantle, diamonds form where pressures crush carbon atoms into their most compact configuration. On K218b, with pressures magnitudes greater, it is plausible, even likely, that carbon coalesces into diamond rain faults, linked from the atmosphere or precipitating from the deep ocean layers. Imagine standing at the edge of an abyss, peering into black waters illuminated by faint bioluminescent life, as solid diamonds, formed naturally from atmospheric chemistry, drift downward like heavy snowflakes, sinking into the depths where heat eventually melts them back into the planetary core. Such a process would create an endless cyclical ballet of carbon, rising through biological activity, falling as solid gems, dissolving again in the hidden furnace below. This extraordinary water world, with its hydrogen-infused seas and mineral rains, would craft alien ecosystems beyond our most indulgent dreams. Earth's ocean life depends on gradients, salinity gradients, oxygen gradients, thermal gradients. On K218b, the dominant gradient would be hydrogen saturation and pressure, both varying dramatically with depth. Entire ecosystems could exist, tiered in layers, each adapted to unique chemical niches, each evolving forms and metabolisms designed to survive and thrive in conditions utterly foreign to us. In the uppermost layers, where light still penetrates the thick atmosphere, strange photosynthetic organisms could flourish. Single-celled or colonial life forms capturing the faint red light of the distant star, converting it into chemical energy, releasing metabolic byproducts back into the atmosphere. Their pigments, unlike chlorophyll's green, would be tuned to the longer wavelengths of red dwarfs, painting the surface waters in hues of indigo or deep crimson. Deeper down, life would change. Chemosynthesis, familiar to Earth's deepest sea vents, might dominate. Organisms could cluster around thermal upwellings, where geothermal energy feeds rich fields of microbes. Some could feed directly on hydrogen, using it as both energy source and nutrient, crafting elaborate biological cycles where waste gases like dimethyl sulfide escape upwards, betraying their presence to distant telescopes like Webb. Further still, at depths where light is but a myth, life forms would have to master extremes of pressure. On Earth, such creatures develop gelatinous bodies, slow metabolisms, and keen chemical senses. On K218b, the adaptations could be grander, creatures with dense, pressure-resistant exoskeletons of exotic biopolymers, organisms that utilize dissolved hydrogen directly in metabolic processes, colonies that drift unfazed by the crushing world above them, forming massive living curtains in the dark. The possibility of floating megastructures of life, vast jellyfish-like organisms kilometers wide, became a subject of genuine speculation. On Earth, siphonophores show how colonial organisms can reach incredible lengths. On K218b, with buoyant hydrogen and endless ocean, the biological canvas is far broader. Perhaps tendrils trail for miles, collecting nutrients, while bulbous upper sacs capture the sparse light, creating a living world within a world. The ocean surface, meanwhile, would be a spectacle of constant chemical activity. Without continents to interrupt flow, currents would span the entire planet, circulating nutrients and heat in great gyres, nurturing vast blooms of microscopic life. Storms, driven by atmospheric dynamics far stronger than Earth's, would whip the ocean into towering waves, churning the interface between atmosphere and sea, mixing biological material and chemicals into an ever-changing soup. Yet, in this turmoil, stability would reign. Life thrives not just on calm, but on reliable cycles, and K218b's atmosphere-ocean system seemed designed for exactly that. Tides pulled by the red dwarf would stir the oceans methodically. Atmospheric pressure would maintain constant temperatures. Ocean currents would ensure global distribution of heat and resources. Life, once established, would not merely survive, it would endure. Evolve and perhaps flourish in ways Earth's brief epochs of stability have never allowed. But not all was gentle. The hydrogen ocean, so nurturing in many ways, could also be treacherous. The immense depth likely created thermal inversion layers, trapping heat and chemicals at certain depths. Violent upwellings might occasionally bring deep, mineral-rich waters to the surface, causing blooms or collapses in local biospheres. Periodic shifts in atmospheric chemistry, perhaps triggered by stellar activity, could send ripples of extinction through the ecosystem, followed by waves of rapid adaptation. Such dynamics would create a living planet in constant flux, yet anchored by deep-rooted stability, a paradoxical world where change was eternal, but life persisted endlessly. As scientists pored over the data, marveling at the atmospheric signatures and the possible ocean dynamics, one truth solidified in their minds. Life on K218b was not an accident of a lucky Earth-like twin. It was the product of a very different set of circumstances, equally capable of fostering biological richness. Our narrow definitions of habitability had been shattered. Life did not require continents. It did not demand nitrogen atmospheres or shallow seas. Under the right pressures, with the right chemistry, in oceans of hydrogen and rains of diamonds, biology could arise, adapt, and perhaps achieve forms more diverse and complex than anything Earth had witnessed. K2N8b's hydrogen oceans whispered this truth across the void, their signals captured by the golden mirrors of Webb, their secrets awaiting future missions to uncover in full. They reminded us once again of the boundless creativity of nature and of our own small place within the grand tapestry of life that the universe was beginning to reveal. Beneath the thick hydrogen clouds of K2N8b, under the faint red glow of its ancient star, an extraordinary idea takes root: life without sunlight. For on this distant world, light is ace. Luxury, scarce and diluted, spread thin across a vast oceanic expanse. On Earth, sunlight has always been life's main architect, its primary energy source. Every leaf stretching skyward, every blade of grass swaying in the wind, every intricate web of the food chain, all trace back to the sun's nourishing rays. But here, on K218b, evolution may have forged an entirely different path, where life thrives not by chasing the light, but by embracing the dark. At first glance, the notion seems paradoxical. After all, K218b resides in its star's so-called habitable zone, warm enough to maintain oceans, active enough to sustain a rich atmosphere. Shouldn't life cling to the limited sunlight available, making the most of every photon that penetrates the atmospheric shroud? Perhaps, but as researchers peered deeper into the spectral data and modeled the planet's conditions, they realized the upper ocean layers, though warmed to a life-sustaining 120 degrees, were bathed in little usable light. The culprit was K2N8b's own protective veil. Its hydrogen atmosphere, dozens of times denser than Earth's, absorbed, scattered, and refracted the limited light of its red dwarf host. The star itself, emitting primarily in the infrared spectrum, was already a feeble lantern compared to our Sun. By the time its rays filtered through the clouds and reached the surface, only a meager trace of light remained, enough to faintly illuminate the ocean's surface, but hardly sufficient to power extensive photosynthetic life as we know it. Yet where traditional life might wither, extremophiles on Earth teach us to expect the unexpected. Our own planet harbors vast communities of organisms that have never known sunlight, microbial ecosystems flourishing in the crushing depths of hydrothermal vents, feeding off chemical gradients rather than solar energy. These earthly life forms metabolize minerals and gases, converting heat and chemicals into sustenance in the utter absence of light. On K218b, this model would likely be the rule rather than the exception. The deep oceans, shielded from radiation, pressed under unimaginable weight, could be the cradle of a life system driven by chemosynthesis, a process where life draws energy directly from chemical reactions, particularly those involving hydrogen, methane, and other simple molecules abundant in the planet's air and water. Scientists speculated with growing excitement perhaps K2N8b's primary life forms are hydrogen-metabolizing organisms. Instead of harnessing photons, they could feed on the immense chemical potential trapped within the hydrogen-saturated ocean. Hydrogen, after all, is a potent fuel. Certain Earth bacteria already utilize hydrogen in anaerobic respiration, generating energy without the need for light or oxygen. On K218b, such a system could dominate an entire biosphere. The implications were profound. Life could exist independently of sunlight entirely, powered by a planet's internal chemistry, limited only by the availability of simple molecules and the gradients they formed. Vast colonies of microbial life could drift through the upper oceans, absorbing dissolved hydrogen, converting it into organic matter, and releasing biological byproducts like methane or dimethyl sulfide, precisely the chemicals Webb had detected. Further beneath the surface, hydrothermal activity could enrich this life web. K218b, with its strong gravitational forces and possible internal heating, might boast geothermal vents along the ocean floor. There, mineral-rich fluids could spew into the water, creating hotspots of activity similar to Earth's mid-ocean ridges. Around these vents, life could cluster in abundance, perhaps even developing complex forms adapted to high pressure and mineral consumption. The ocean's vertical structure would foster specialization, just as Earth's marine life differentiates in Tophotic, mesopelagic and bathypelagic zones. K208b's inhabitants might evolve in layers. Near the surface, light-starved but heat-rich regions would support vast blooms of chemotrophs, forming drifting microbial mats or gelatinous colonies. Mid-depth zones might host filter-feeding organisms, slowly sifting the nutrient-dense waters for sustenance. In the abyssal plains, deep-dwelling organisms, possibly armored against crushing pressure, could feast upon mineral flows and thermal energy. And still, there was another twist: tidal flexing. K218b's orbit around its red dwarf was likely tidally locked, with one face forever gazing at its star and the other cast in eternal night. But gravitational forces, especially from a potentially complex system of moons or nearby planetary bodies, could cause periodic tidal flexing. This flexing would generate internal heat, fueling geothermal processes and enhancing the chemosynthetic potential of the oceans. Imagine towering underwater mountains spewing fountains of mineral-laden water. Imagine deep-sea trenches where the pressures crushed ordinary molecules into exotic, high-energy compounds. Life in these environments wouldn't just survive, it could flourish in densities unheard of on Earth. The planet's oceans, vast and uninterrupted, would offer a playground for biological expansion on a scale beyond terrestrial comprehension. Moreover, the absence of photosynthesis need not preclude complexity. Earth's hydrothermal vent ecosystems show startling diversity: giant tube worms, bioluminescent shrimp, symbiotic colonies. On K218b, with its greater pressure, temperature stability, and chemical richness, life could evolve forms adapted to efficiency, longevity, and perhaps even intelligence, all without ever glimpsing the stars. Some biologists dared to dream bigger. Could complex multicellular life arise in such environments? Could organisms develop intricate sensory systems adapted to the pressure and chemical gradients rather than light? On Earth, certain cave species have evolved echolocation in total darkness. Deep-sea creatures navigate by electric fields or subtle vibrations. On K218b, evolution might favor similar adaptations: sonar-like communication, electromagnetic perception, pressure-sensitive locomotion. Bioluminescence, too, could play a starring role. In Earth's oceans, light is a rare and valuable tool for communication, predation, and camouflage. On K218b, with its darkened depths and muted daylight, organisms could harness internal chemical reactions to generate light, flashes, pulses, or glows that signal across vast, otherwise empty expanses. Great tendrils could light up the depths in swirling dances of color, while predatory creatures might lure prey with mesmerizing displays. Even higher-level behaviors seemed plausible. Communal living, cooperation, perhaps even proto-societies could evolve among intelligent marine organisms, sharing resources, migrating in coordinated schools, crafting intricate mating rituals, or establishing rudimentary forms of culture. If intelligence could arise independently of sunlight, it would rewrite our assumptions about the pathways to sentience. All of this led to a staggering conclusion. The presence of life-suggesting gases in K208b's atmosphere was not merely a fluke of chemical equilibrium. It could represent the atmospheric exhalation of a global, multi-tiered, thriving biosphere, a living world humming beneath a canopy of clouds, singing in biochemistry, hidden from our eyes but screaming its existence through spectral signatures. In Earth's history, sunlight was essential because it was abundant. On K218b, life had chosen, or been forced, to chart a different course. It showed humanity that life was not bound to the light. It could originate and flourish in places where sunlight never touched, in oceans wrapped in darkness but alive with chemical energy. For astrobiologists, it was both exhilarating and humbling. If life could thrive without sunlight, the universe's potential teemed with possibility. Countless exoplanets previously dismissed as too dim, too cold, or too hidden now demanded fresh attention. The search for life expanded, encompassing worlds beneath ice shells, oceans trapped under miles of crust, and planets shrouded in hydrogen and perpetual cloud. K218b was no longer merely an anomaly, it was a guidepost, a living testament to the adaptability of life. In its quiet darkness, it whispered a truth far older and grander than humanity. Life finds a way, not always by reaching for the light, but sometimes by learning to glow in the dark. In the intricate orchestra of atmospheric chemistry, every molecule plays its part, humming in harmony or clashing in discord. On K218b, amid the dense hydrogen skies and the warm, heaving oceans, one gas stands out as an insistent, repetitive note, a whisper that refuses to be silenced. Methane, simple in structure, one carbon bound to four hydrogens, and yet, in the context of life, profoundly significant. It is a molecule that can be born from volcanic fury or from the breath of living things. But here, on this distant world, methane flows in such abundance, in such persistently elevated concentrations, that it refuses to be dismissed as merely geological background noise. The James Webb Space Telescope had caught it first, its golden mirrors filtering starlight through the clouds of K218b, unraveling the spectral fingerprints with exquisite precision. Dimethyl sulfide may have been the headline, the molecule that screamed biological origin, but methane lingered throughout the data, abundant, active, replenished continuously despite conditions that should, by logic, have broken it down. Methane on Earth is fleeting. It survives briefly in the atmosphere, easily oxidized by interactions with ultraviolet light and reactive hydroxyl radii. Chaos. In an environment without constant replenishment, methane disappears swiftly, swallowed by photochemical reactions. On barren worlds like Mars, traces of methane vanish as quickly as they emerge, leading scientists into cycles of excitement and disappointment. Yet on K218b, methane sang steadily, a persistent, unwavering note in the grand cosmic song, signaling that something active and robust was feeding it into the atmosphere with relentless consistency. What could maintain such levels of methane across the centuries? The simplest answer pointed upwards, towards geochemistry. Volcanic activity, the exhalation of a planet's molten interior, can release methane in surges. Yet K218b's spectral fingerprint didn't merely indicate methane spikes, it showed equilibrium, stability, a continuous presence that defied the short, violent pulses of volcanic release. Furthermore, the atmosphere was rich in carbon dioxide, water vapor, and hydrogen, but lacked the sulfur dioxide and other volcanic byproducts typically expected from geologic outgassing. There remained only one plausible explanation: life. Biological processes, invisible to our distant eyes, were crafting methane within K218b's oceans and casting it skyward in plumes and streams. Microbial life, known on Earth to release methane through anaerobic digestion, could flourish in the warm, stable depths of the planet's oceans, breaking down organic compounds in cycles millions of years old. Imagine, if you will, a vast ocean teeming with microbial colonies, living in layers defined by pressure and chemical gradients. Near the surface, photosynthetic or chemosynthetic organisms absorb minerals and dissolved gases, metabolizing them into simple sugars and proteins. As these organisms die, their bodies drift into the depths, decomposing under the heavy pressure. Microbial life in the abyss consumes this organic detritus, breaking it down in oxygen-starved environments, releasing methane as a byproduct into the water column from T. Here, methane seeps into the atmosphere, rising through the ocean in shimmering bubbles, bursting into the sky where Webb catches their spectral trace. But this was only the beginning of the methane story. Some researchers speculated on grander, more complex biological networks. What if, beneath the hydrogen-rich sea, there existed organisms adapted specifically to channel methane for energy? Earth's methane-consuming archaea, called methanotrophs, thrive in niches where methane is abundant. They consume it, oxidize it, and integrate it into cellular metabolism. On K218b, such organisms could function at scale, not merely surviving but flourishing, feeding vast ecosystems within the nutrient-rich depths. An intricate web could exist, methane-producing life in the deep sediments, methane-consuming life in the mid-level ocean, and specialized species near the surface, capturing the remains of these processes. The atmosphere, far from a chaotic stew, would be the outward expression of this internal biosphere, a dynamic yet balanced cycle of production and consumption. Even more intriguing was the prospect of methane clathrates, solid structures where methane is trapped within ice-like lattices under pressure. On Earth, such formations exist in deep-sea sediments and under permafrost, occasionally releasing large quantities of methane into the atmosphere in sudden planet-shaping events. On K218b, the combination of high pressure, hydrogen saturation, and deep, cold ocean layers could foster massive methane reservoirs, slowly leaking gas into the ocean and air, perhaps regulated by microbial processes. Could there be seasons of methane dictated not by axial tilt but by internal ocean currents? Could planetary tides flex and squeeze the ocean crust, releasing periodic methane blooms that recharge the atmosphere every planetary year? Webb's continuous monitoring showed no slur. Seasonal variation, suggesting a steady-state system, but the tantalizing possibility of deeper, more complex cycles lingered. Astrobiologists embraced this discovery with a renewed sense of purpose. On Earth, methane had become an atmospheric biosignature, one of the clearest potential indicators of life. Yet here, in K218b's thick skies, methane told a more sophisticated tale, not just of life's existence, but of its dominance, its global integration into planetary processes. The levels of methane detected couldn't be explained by sporadic life or isolated ecosystems. This was not a planet where life barely clung to survival. It was a thriving world, rich in biological activity, where life's breath shaped the entire atmospheric chemistry, visible from across the cosmos. Methane's stability also pointed to environmental harmony. No catastrophic oxidizing events seemed to plague the atmosphere, no violent shifts that would decimate life's delicate cycles. Instead, there was a slow, steady churn, a heartbeat of methane rising and falling gently, maintaining an equilibrium indicative of a long-term, stable biosphere. This realization transformed how scientists viewed K218b. No longer a lonely rock orbiting a distant star, it emerged as a robustly living planet, communicating through chemical whispers that traveled light years to our observatories. Every spike in methane, every trace of dimethyl sulfide, every balanced proportion of carbon dioxide and water vapor spoke of a mature, interconnected world where life had flourished long enough to leave a detectable imprint on the atmosphere. It forced a re-examination of our own world's early history. Billions of years ago, Earth's atmosphere brimmed with methane, shaped by ancient microbial mats and oceanic blooms. Before oxygen ever painted our skies blue, Earth had been a methane world. K208b, in some distant mirror of history, might represent an ancient Earth analogue, forever suspended in a stage of biological development we once passed through, or perhaps thriving in it in ways we failed to achieve. What future awaited such a world? Would methane continue to rule the atmosphere for eons? Could life evolve complexity, intelligence, or technological civilization without ever transitioning to an oxygen-rich world? Or was methane's dominance the endpoint for K218b, a beautiful, self-sustaining microbial Eden, content in its simplicity, unconcerned with the complexities of cognition and culture? For now, these were only questions, shimmering just out of reach, hiding beneath the hydrogen clouds and the unfathomable oceans. But the presence of methane had given humanity something more precious than certainty. It had given hope, a quiet validation that life could be abundant, diverse, and persistent across the galaxy. K218b breathed methane into the void, and with every passing year, every photon captured, that whisper grew louder in human ears. It was a reminder that the universe's default state may not be silence, but life, thriving, enduring, endlessly creative life, waiting patiently for us to listen. In the vast, untamed wilderness of the cosmos, gravity is both creator and captor. It gathers stardust into suns, molds gas into planets, binds moons in their endless circuits, and sculpts galaxies into swirling spirals of light. Yet for life, gravity can be a double-edged force, cradling the fragile chemistry of existence while simultaneously locking it within a finite domain. On K218b, gravity's role is profound and unforgiving, exerting a relentless pull that is 3 times stronger than Earth's, crafting a world where every drop of ocean, every wisp of air, and every living thing exists under the quiet weight of a cosmic embrace. To stand upon the surface of K218b, if such a surface could be found beneath its boundless oceans, would be to feel the crushing grip of this gravitational force pressing down with intensity, beyond terrestrial experience. An earthly body accustomed to gentle resistance would be rendered motionless, pinned by invisible hands. Limbs would tremble, hearts would strain, bones would creak under the tripled load. But for native life, gravity would not be a hindrance. It would be the sculptor of strength, the author of biological blueprints uniquely tuned to the demands of a heavy world. K218b's gravity ensures that its atmosphere, thick and immense, clings tightly to the planet's surface, resisting the ravages of stellar winds and cosmic radiation. Where Mars lost its atmosphere to the sun's fierce breath, K218b's skies remain intact, hugged close by gravity's ceaseless pull. This protective cocoon allows the rich chemical symphony detected by James Webb to endure. Methane, dimethyl sulfide, water vapor, carbon dioxide, all cradled within the gaseous envelope, swirling gently above oceans that ripple beneath crushing skies. But gravity's influence does not end with the atmosphere. It extends deep into the oceanic world, shaping the layers of life from surface to abyss. Pressure, a direct child of gravity, increases with startling speed on K218b. Every descent into its watery depths would be met with accelerating compression, creating environments where only the hardiest, most pressure-adapted life could thrive. Earth offers a modest reference. At the deepest point of the Mariana Trench, pressure reaches 1,100 atmospheres. On K218b, equivalent depths would bring unimaginable forces, perhaps thousands of atmospheres pressing down upon any life below. Yet, as Earth's own deep-sea extremophiles reveal, life is astonishingly flexible. On K218b, evolution would embrace the challenge, favoring biological designs that turn crushing pressure into an advantage. Life here would likely be compact, dense, and resilient. Flimsy structures would collapse, delicate tissues would rupture. Instead, organisms would. You would evolve reinforced cellular walls, pressure-resistant biochemistries, and perhaps entirely novel biological architectures. Internal cavities might be minimal or pressurized to prevent collapse. Movement, too, would adapt, graceful gliding over rapid bursts, muscles honed to efficiency under constant strain. Floating life forms could develop gas-filled bladders, not with nitrogen or oxygen, but stabilized hydrogen pockets carefully tuned to the extreme ambient pressure. These bladders would not provide buoyancy in the traditional sense, but allow for fine-tuned vertical migration, rising to sunlit zones or descending into nutrient-rich depths as needed. The ocean currents themselves, driven by gravitational forces, would be massive and persistent, churning across the globe in unbroken circulation. Without continents to interfere, gyres would form that spanned hemispheres, transporting heat and nutrients from dayside to nightside, from equator to poles, fostering a uniformity of conditions that supported vast biological abundance. Yet the true mystery lay in how such gravity might influence complexity, behavior, and even intelligence. On Earth, the evolution of complex life was shaped by mobility, by the ability to chase prey, to escape predators, to explore diverse habitats. Would K208b's life, constrained by gravity, remain limited to simple forms, or would evolution forge pathways around these physical limitations? Some researchers imagined a world where intelligence evolved not through movement but through collaboration. Dense, slow-moving colonies of organisms could develop communal behaviors, exchanging chemical signals across the ocean, creating networks of shared knowledge without ever needing to travel far. Stationary filter feeders could evolve sophisticated sensory systems capable of mapping their environment through vibration and chemical detection, forming a static yet intellectually rich society beneath the waves. Alternatively, life may have developed ways to resist or mitigate gravity's grip. Perhaps in the upper atmosphere where pressure is lower and buoyancy easier to achieve, aerial plankton-like organisms float endlessly, drifting on high-altitude winds, exchanging genetic material, nutrients, and even proto-linguistic signals through bioluminescence or chemical release. The gravitational effects extended even further into the evolution of metabolic processes. Higher gravity meant denser fluids, faster heat transfer, and possibly more efficient chemical mixing. Biological reactions could proceed at enhanced rates, potentially accelerating evolutionary processes. Adaptations that might take millions of years on Earth could emerge in tens or hundreds of thousands of years on K218b, driven by the dynamic interplay of pressure, chemistry, and energy availability. Geologically, K218b would also bear the marks of its intense gravity. The ocean floor would be smoother, with less dramatic mountain ranges due to the relentless pull-flattening geological formations. Volcanic activity, if present, would manifest through powerful deep-sea eruptions, injecting mineral wealth into the oceans but perhaps rarely reaching the upper atmosphere. Gravitational locking, too, shaped the world. K218b, bound in tidal embrace with its star, presented the same face to its sun at all times, creating an eternal hemisphere of daylight and one of perpetual night. But gravity's gentle prison ensured that these hemispheres were not isolated. Atmospheric and oceanic circulation erased the sharp boundaries, distributing warmth across the planet, enabling habitability even in regions untouched by direct sunlight. The absence of rotational cycles, day and night transitions, would deeply influence behavioral rhythms. On Earth, life dances to the circadian drumbeat, guided by sunrise and sunset. On K218b, its cycles would be dictated by chemical availability, by nutrient flows, by internal biological clocks evolved to the planet's unique environment. Time, as experienced by living organisms, would take on new meaning. Perhaps in this world of constant gravity, life learned to measure time through chemical cycles, through tidal flexing, or through subtle variations in atmospheric composition. Entire species might possess an innate sense of planetary rhythms, synchronized not to spinning orbits but to gravitational pulses. Even in the hypothetical development of technology, gravity's influence could not be ignored. Terrestrial civilization was enabled by fire, by metallurgy, by mobility, concepts tied to the manipulation of solids and gases in low-pressure environments. On K218b, technological development, if it occurred, would likely emerge within the ocean, using chemical processes, bioengineered structures, or perhaps even harnessing geothermal energies. Mobility would be slow, construction limited to what materials and physics allowed under crushing pressure. Or perhaps intelligence would express itself not through tools, but through knowledge transfer, genetic, chemical, or communal, an intelligence of biological adaptation rather than mechanical invention. Gravity shaped everything: the depth of oceans, the thickness of the sky, the forms of life, the rhythms of existence. Yet it also protected, nurtured, and stabilized. K218b's atmosphere remained thick, its oceans warm, its biosignatures persistent, all because gravity refused to loosen its grip. From across the cosmos, humanity observed the influence of this gentle prison and marveled. On Earth, life's fragile chemistry depended on narrow environmental tolerances. On K218b, life seemed to have adapted to and perhaps thrived under constant, inescapable pressure, and in that realization there emerged a deeper truth. Life is not confined by comfort. It does not wither under force or perish under weight. It adapts, transforms, finds ways to endure. Even in the deepest trenches, beneath the heaviest skies, life persists, not in defiance of gravity, but in partnership with it. Gravity's gentle prison was not a cage, it was a cradle. Suspended in the vast emptiness of the galaxy, K218b orbits a star that is far removed from the grandeur of our Sun. It does not blaze with brilliant white light. It does not warm its system with radiant intensity. Instead, it glows quietly in deep crimson, a red dwarf star known to astronomers as K218. Modest in size, humble in energy output, but ancient beyond imagination, this star is a sentinel of the cosmos, a celestial elder destined to outlive countless generations of stars like our own. It is a star that in human timescales never dies. On Earth, life arose under the gaze of a volatile, middle-aged G-class star, a sun that burns hot and bright but will inevitably burn out. Our world's entire evolutionary history, from the earliest microbial stirrings to the complex web of modern ecosystems, has unfolded under the ticking clock of solar life expectancy. In 5 billion years, the sun will swell, devour the inner planets, and reduce Earth to a lifeless ember. Yet, on K218b, the story unfolds differently. The star it orbits does not suffer the same destiny. Red dwarfs, like K218, are the universe's patient guardians. They burn their hydrogen fuel slowly, efficiently, stretching their lifespans into the trillions of years. While massive stars live fast and die young, exploding in brilliant supernovae after a few million years, red dwarfs smolder in quiet endurance, outlasting the cosmos itself. In fact, not a single red dwarf has yet died in the observable universe, because the universe itself is not old enough to have seen one reach the end of its life. This remarkable longevity casts K208b's potential habitability in a new, extraordinary light. While life on Earth races against AS, shrinking clock, life on K218b, if it has arisen, may have more time than we can comprehend. Billions of years are merely the opening chapters, trillions await. The possibility of life persisting, evolving, and adapting over such unfathomable epochs is both staggering and humbling. For astrobiologists, this longevity is not a trivial detail. It is central to understanding life's cosmic distribution. One of the oldest questions in science asks, how long does it take for life to arise? The answer, according to Earth's history, is surprisingly quick. Life began within a few 100 million years of the planet's formation. But complex life, intelligent life, these took billions. On Earth, time is a limiting resource. Cataclysmic events, solar aging, and tectonic instability impose ceilings on biological progress. K218's long-lived nature removes that ceiling. Life here, given favorable conditions, may have the luxury of uninterrupted time to evolve, diversify, and perhaps even transcend biological limitations. Civilizations could rise and fall not once, but 1,000 times, with the star's patient red glow persisting unchanged through their entire history. And it is not just time that makes K218 unique, but its stability. Our Sun, though comparatively stable, experiences fluctuations, solar flares, coronal mass ejections, magnetic cycles that periodically threaten Earth's fragile technological civilization. Red dwarfs, while known for youthful outbursts, settle into an extended maturity marked by tranquility. K218, by the data gathered through long-term monitoring, appears to be such a mature, quiet star, its flaring days long past, its activity reduced to gentle hums of electromagnetic radiation. This stellar quietude has profound implications for planetary habitability. On many worlds, particularly those orbiting young red dwarfs, frequent flares strip atmospheres bare, bombard surfaces with lethal radiation, and sterilize the upper layers of oceans. But K218b, blessed by the serenity of its aging star and shielded by its own massive atmosphere, escapes this grim fate. Its air remains intact, its oceans warmed but not scalded, and its biological signatures flourish under the crimson glow of a star that grants safety and time in equal measure. The spectrum of light that K218 emits is skewed heavily towards the infrared, lacking the intensity of visible light that fuels Earth's photosynthesis. Yet this too is no barrier. Life adapts. On Earth, certain microbes thrive in low-light environments utilizing alternative pigments that harvest infrared wavelengths. Photosynthetic pathways tuned to K218's spectral output could drive energy cycles on K208b's oceans, supporting robust ecosystems even in the absence of bright, visible light. Moreover, the planet's proximity to its star, the close orbit necessitated by the star's low energy output, creates a unique gravitational intimacy. Tidally locked, K218b shows one face forever to its star, basking in perpetual twilight, while the opposite hemisphere remains cloaked in endless night. This configuration, stabilized over geological timescales by K218's unwavering gravity, fosters constant conditions ideal for life to gain a foothold and persist without the destructive upheavals of frequent orbital changes. The combination of a quiet, eternal star and a thermally balanced world creates a setting where life's only adversary is itself. Not the chaotic whims of stellar fury, not the slow death of a sun, but the internal rhythms of biology and evolution. Some scientists have dared to speculate, if life on Earth has endured for 4 billion years, what heights could it reach in 10, 100, or 1,000 billion years under a star like K218? K218's cosmic patience opens the door to possibilities well beyond our familiar frameworks. Civilizations, should they emerge, would have the gift of planning, millennia, of mastering sciences we cannot yet imagine, of exploring not just neighboring star systems but the distant reaches of the galaxy, secure in the knowledge that their parent star will shine steadily for ages untold. Even without intelligence, the biosphere itself could climb levels of complexity unseen on Earth, where evolutionary pressures are too compressed. On K218b, macroevolutionary experiments could unfold over tens of millions of years without interruption. Symbiotic relationships could refine into near perfection. Genetic diversity could expand exponentially, filling every ecological niche in the vast oceanic environment. Adaptations could evolve beyond survival, toward thriving in optimal conditions where energy is steady, habitats are stable, and environmental catastrophes are exceedingly rare. There is, however, a haunting beauty to the implications of such stellar longevity. In the distant future, after the Milky Way collides with the Andromeda Galaxy, after the last white dwarfs fade, after even Earth's memory is extinguished, it will be red dwarfs like K218 that persist, illuminating the cold, quiet galaxies. Their ancient planets, if life survives, could be among the last strongholds of biology in a universe winding down toward entropy. Perhaps in the twilight of the cosmos, it will be K218 and stars like it that host the final embers of living thought, the last flickers of evolution's grand experiment. Life's ultimate refuge may not be around grand suns, but around humble, steadfast red dwarfs, their energy stretched thin but enduring through cosmic ages. For humanity, peering across 120 light-years through the eyes of the James Webb telescope, K218 offers both a revelation and a mirror. It shows us what it means to be young in a universe where age is counted in trillions. It reminds us of our own fleeting moment in the cosmic time line and invites us to dream of civilizations that need not be ephemeral, of life that need not end within the brief flare of a single sun. As we listened to the whispers of K218b's atmosphere, as we marveled at the balance of its oceans and the quiet endurance of its star, we understood a deeper truth. Our search for life is not just a quest for companionship, but a yearning for continuity. K218 and its world promise us that life's story need not be short, that the universe itself holds chapters far longer, far richer than anything we have yet imagined. The star that never dies waits in the depths of Leo, its light ancient, its patience infinite, its planet possibly alive, possibly vibrant, and perhaps one day capable of answering back. In the early days of exoplanet discovery, the scientific consensus was narrow, shaped by the single blueprint we knew: Earth. For decades, the search for life fixated on pale blue dots orbiting sun-like stars, planets with rocky surfaces, nitrogen-oxygen atmospheres, and conditions that mirrored our own terrestrial cradle. Super-Earths, like K2-188b, were dismissed as unlikely hosts for life. Too large, too gaseous, too strange, they were seen as half-formed gas giants or miniature versions of Neptune, places of storm-ravaged skies and crushing gravity, where life, if it existed, would be fleeting or primitive. But K2-188b shattered those expectations with one elegant revelation after another. It became a living contradiction to humanity's early models, a super-Earth with an ocean, an atmosphere enriched with biological gases, and surface temperatures flirting with the range that sustains complex chemistry. The more scientists peered into the veiled mysteries of K2-188b, the clearer it became. This world, by all rights ignored or underestimated, could be a biological jewel in the galaxy. It was a humbling realization. The universe, in its quiet complexity, had resisted our simplistic categorizations. Instead of behaving like a mini Neptune, K2-188b revealed itself as a Hycean world, a new classification that defied traditional thinking, a hybrid, hydrogen-rich yet water-abundant, massive yet nurturing, hostile in some aspects but life-favoring in others. The discovery cracked open the door to an entirely new paradigm in planetary science. At the heart of this revelation was the simple yet revolutionary understanding that mass does not determine destiny. K2-188b, with a mass over 8 times that of Earth and a radius more than twice as large, had been presumed to harbour an inhospitable atmosphere, its gravity trapping thick clouds of gas and preventing the delicate balances required for life. But the James Webb Space Telescope painted a more nuanced picture, one of balance rather than chaos, of heat regulation rather than thermal runaway, of atmospheric chemistry in delicate equilibrium. Such stability arose from an unexpected convergence of factors. First, the planet's location in the habitable zone of a red dwarf star ensured gentle, constant warmth. Second, its gravitational embrace prevented atmospheric escape, maintaining the very gases that supported temperature moderation and chemical cycling. Third, the thick atmosphere, far from suffocating life, acted as a protective shell, regulating temperatures, blocking harmful radiation, and allowing the oceans to exist in liquid form. And it wasn't just stability that defied expectation, it was the atmospheric composition itself. Scientists had long assumed that super-Earth atmospheres would be dominated by primordial gases, thick with inert or suffocating molecules, sterile to biological processes. But K2-188b offered an atmosphere alive with activity: methane, water vapor, carbon dioxide, and dimethyl sulfide, molecules linked on Earth to metabolic activity and biological output. This unexpected atmospheric cocktail transformed K2-188b from a speculative rock into a living laboratory. It forced scientists to reconsider assumptions about what atmospheres signify and how life may modify its environment in detectable ways, even on worlds that seem too large, too dense, or too alien to host life. K2-188b also challenged expectations about tidal locking. The perpetual day and night sides of such planets were feared to create hostile dichotomies, scorching deserts on one side and frozen wastelands on the other. Early atmospheric models warned of atmospheric collapse, where gases would freeze on the night side, creating uninhabitable worlds. Yet on K2-188b, the atmospheric data suggested vigorous circulation that redistributed heat effectively, preventing catastrophic cooling or overheating. Such revelations had a cascading effect on exoplanet science. Suddenly, the inventory of potentially habitable worlds expanded exponentially. Super-Earths, previously dismissed by some as oversized barren rocks, were reclassified as prime candidates for life. The traditional Earth-like Goldilocks zone grew broader, encompassing planets with diverse sizes, compositions, and atmospheric configurations. With K2-188b, the scientific community realized that life's playground was not a narrow field, but an entire landscape of unexpected forms. Life could arise not only in Earth clones, but in massive ocean worlds, beneath hydrogen skies, in perpetual twilight under faint red suns. The discovery prompted a re-evaluation of older exoplanetary data. Worlds once catalogued and passed over were re-examined with fresh eyes. Astronomers revisited archived spectroscopic readings, seeking signatures of water vapor or biological gases in places previously deemed too extreme. The quiet message of K218b, "Do not assume, observe," rippled across observatories, prompting renewed exploration of red dwarf systems, distant planetary giants, and everything in between. Beyond the scientific implications, K218b challenged the philosophical foundations of humanity's place in the cosmos. The assumption that life required Earth-like conditions had always carried with it an element of anthropocentrism, the belief that it's our form of life, our type of world, was the universal standard. But here, floating in a distant system, was proof that life-friendly conditions could emerge in environments wildly different from our own. Life, it seemed, was not beholden to our preferences. It adapted to whatever canvas the universe provided. For planetary scientists, this realization was both liberating and daunting. It expanded the catalogue of potentially habitable worlds into the tens of billions within our galaxy alone. Every red dwarf, every super-Earth, every atmospheric reading became a potential clue in a vast interwoven mystery. K218b was not merely an outlier, it was the first chapter in a rewritten textbook, a starting point for a new age of discovery. Even the technological narrative shifted. The instruments designed to search for Earth-like planets were being repurposed to investigate a broader spectrum of possibilities. New missions were proposed to focus specifically on Hycean worlds. Ground-based observatories fine-tuned their detection methods to capture faint, low-energy signals from planets orbiting small, quiet stars. Machine learning algorithms were deployed to sift through the petabytes of exoplanetary data, hunting for subtle hints of unexpected habitability. K218b stood at the heart of this renaissance. Its atmospheric fingerprints, carefully traced by the Webb telescope, became a template for what to look for on other worlds. Dimethyl sulfide, once a molecule of obscure biological relevance, entered the lexicon of astronomical biosignatures. Methane, often dismissed as ambiguous, gained fresh credibility when considered in the right atmospheric context. Water vapor, long known as a marker of potential, took on renewed importance when found in concert with other biological markers. Astrobiologists, once limited by the narrow Earth-centric framework, embraced the challenge of imagining ecosystems in exotic conditions. Entire conferences were dedicated to speculative biology, how life might metabolize hydrogen, how chemosynthesis could dominate vast aquatic environments, how evolution might proceed in perpetual warmth and darkness. Interdisciplinary collaborations emerged, blending oceanography, evolutionary biology, atmospheric science, and planetary geology in unprecedented ways. Even the cultural impact was profound. K218b captured the public's imagination, appearing in documentaries, novels, and artistic renditions. It became a symbol of cosmic humility, a reminder that the universe is far more diverse and mysterious than early explorers had dared to dream. Students studied its characteristics as a gateway to understanding the expanding frontiers of science. Filmmakers visualized its endless oceans and crimson skies. Philosophers pondered what it meant to know that life could thrive in places so alien to us. In every corner of human society, K218b whispered its quiet lesson. Expect the unexpected. The universe is not bound by our preconceptions, nor is life restricted to the narrow parameters we once thought immutable. When planets defy expectations, humanity is forced to grow, not only in knowledge but in imagination. K218b opened the doorway to a broader, richer universe. And through that doorway, generations of explorers, scientists, and dreamers would step, forever changed by the realization that life's potential is as vast and boundless as the stars themselves. In humanity's ancient history, our ancestors gazed up at the night sky with eyes alone, naked and vulnerable, limited by the narrow spectrum of visible light. They charted stars, told stories of constellations, and measured seasons by celestial motion. Yet the true secrets of the cosmos remained hidden, dancing invisibly beyond the reach of our primitive senses. It took generations, millennia, to forge tools that could peel back the layers of darkness. And today, orbiting far beyond the confines of Earth's atmosphere, we possess eyes unlike any in human history. Eyes that see the unseen, that read the language of distant planets, that whisper of life across unimaginable distances. Chief among them is the James Webb Space Telescope, the golden sentinel that turned its attention toward K218b and for the first time let humanity glimpse the invisible breath of an alien world. Webb is no ordinary telescope. It is not limited to visible wavelengths like its predecessors, nor constrained by Earth's turbulent atmosphere. It operates in the infrared, perceiving the universe in a heat map of ancient light and chemical fingerprints. Its massive honeycomb-shaped mirrors gather photons that have traveled for centuries, their subtle energies too faint, too elusive for ordinary instruments to capture. And with this exceptional sensitivity, Webb transformed K218b from a silent point of data into a living, breathing world. From its vantage point a million miles from Earth, at the tranquil gravitational equilibrium known as Lagrange Point 2, Webb hovers in perpetual shadow, shielded from the thermal noise of our planet and the Sun. Here, in the cold silence, it listens to the cosmos, capturing the whispers of starlight as it filters through alien atmospheres. The key to K218b's revelation lay in a technique known as transmission spectroscopy, a method elegant in concept yet monumental in execution. As K218b passed in front of its parent star, a portion of the star's light passed through the planet's atmosphere before reaching Webb's detectors. In this brief periodic alignment, the planet revealed itself, not in reflected light, but in the way it altered the starlight that touched it. Every molecule in the atmosphere absorbed certain wavelengths of light, creating minute but measurable dips in the spectrum. Like a prism breaking sunlight into a rainbow, K218b's atmosphere stamped its molecular identity onto the star's glow. Webb, with its unprecedented sensitivity, read this spectrum with astounding precision, decoding the invisible composition of a world light years away. The resulting data was nothing short of historic. Patterns of water vapor arced through the readings, announcing the presence of vast hydrogen-laced oceans. Methane carved distinctive signatures, persistent and abundant, indicative of biological or at least active chemical processes. Dimethyl sulfide, on Earth a byproduct of living organisms, appeared faintly but unmistakably, a potential biosignature reaching out across space. Carbon dioxide revealed itself, suggesting a dynamic planetary carbon cycle. Each molecule, each spectral line, told a piece of K218b's story. Before Webb, such a revelation would have been science fiction. Even the great Hubble, perched in low Earth orbit, lacked the power to resolve the atmospheric intricacies of such distant small planets. Ground-based telescopes blurred by atmospheric distortion could only hint at such compositions, but Webb's vast mirror, nearly 6.5 meters in diameter, combined with cryogenically cooled instruments, provided clarity never before achieved. It is important to understand just how delicate these observations are. K218b's light, even at its brightest, is infinitesimal, a billionth the brightness of its host star. Detecting its spectral fingerprints required collecting thousands of transits, compiling weeks of data, and accounting for noise from distant cosmic radiation, stellar activity, and instrumental variation. Yet Webb achieved the near impossible, extracting coherent, reproducible signals that painted K218b not as a featureless dot, but as a complex, dynamic world. Moreover, Webb's suite of instruments allowed for multidimensional observation. Its near-infrared spectrograph, NIR spec, passed fine details of molecular absorption bands. Its mid-infrared instrument, MIRI, reached deeper into the thermal profile of the atmosphere, revealing heat distributions and thermal gradients. Its near-infrared imager and slitless spectrograph, NIRIS, aided in exoplanet transit observations with high precision. Together, these instruments formed a symphony of detection, capturing K218b's atmospheric dance in ways unimagined just decades ago. But Webb did more than observe. It ignited a shift in our understanding of the cosmos. Through its eyes, astronomers discovered the diversity of planetary atmospheres across a growing list of exoplanets. Some worlds revealed scorching, metallic skies, others unveiled atmospheres rich in silicates or sulfuric acid. And then there was K218b, quiet, balanced, alive with potential. Its hydrogen-rich skies, punctuated by water vapor and life-linked molecules, stood as a gentle anomaly in a cosmos filled with chaos. Webb's insights prompted a cascade of scientific questions. What atmospheric dynamics sustained K2-8b's chemical equilibrium? Could unseen geological activity contribute to its spectral signature? Was there a biological feedback loop enriching its atmosphere over millennia? Each answer yielded new hypotheses, driving an era of discovery where telescope time became the most coveted resource in modern science. The observations also forced planetary modelers to innovate. Complex three-dimensional simulations sprang up in university labs and research institutes, using Webb's data as anchoring points to explore atmospheric circulation, ocean dynamics, and potential biospheres. K218b, once an unremarkable catalogue number, evolved into a digital world recreated in supercomputers, its winds charted, its clouds modelled, its oceans animated in rich visualizations. More telescopes would soon follow Webb's path. Missions like the European Space Agency's Ariel and NASA's proposed Habitable Worlds Observer. Tory took inspiration from Webb's triumph, focusing their design on wide-scale atmospheric characterization of exoplanets. Ground-based observatories like the Extremely Large Telescope prepared to peer into these distant atmospheres with complementary wavelengths, expanding humanity's sensory reach further still. Yet even amid these future promises, Webb remained the pioneer, the first eye to gaze into K2-8b's heart and reveal its secrets. In broader cultural consciousness, Webb symbolized more than scientific progress. It embodied humanity's yearning to see beyond its limitations. Webb was the answer to ancient prayers uttered beneath naked skies, the fulfillment of dreams that stretched back to the earliest astronomers. Its ability to see the unseen connected the technological present to the stargazing past, weaving a continuous thread through history. For the search for life, Webb's observations proved transformative. They demonstrated conclusively that atmospheric biosignatures could be detected across interstellar distances, breaking the final barrier between humanity and its ancient cosmic question. Are we alone? No longer restricted to theory, no longer trapped by technological ceilings, humanity possessed eyes capable of observing life's echoes, however faint, in the atmospheres of far-flung worlds. And with each new observation, K2-8b continued to speak. Not in sounds, not in radio waves, but in the spectral symphony of molecules, in the quiet thermal glow of oceans, in the rhythmic transit across its enduring star. Webb listened, humanity listened, and for the first time in history, the silence of the cosmos seemed a little less absolute. In the golden mirrors of Webb, humanity glimpsed not only the details of a distant exoplanet, but a reflection of its own persistence. A reminder that across vast obstacles of distance, time, and limitation, curiosity endured, evolved, and overcame. The eyes that see the unseen had opened, and the universe, long patient in its quiet grandeur, began to answer back. In the realm of cosmic discovery, there are moments driven by wonder, by the sweep of telescopes and the poetry of stars. But beneath the poetry lies mathematics, silent, precise, unfeeling in its calculations. Numbers do not dream, they do not hope, yet they have the power to change everything. On Earth, civilizations have risen and fallen by mathematics, through navigation, architecture, astronomy, and industry. And now, in the quiet corridors of exoplanet research, it was math that delivered the most profound message from K2-8b, not through dazzling images or dramatic flashes of light, but through the unrelenting certainty of statistical truth. When the James Webb Space Telescope captured the spectral signatures bleeding through the atmosphere of K2-8b, scientists did what they always do. They counted, analyzed, and calculated. Thousands of spectral lines, thousands of photons, each a messenger from a world 120 light-years away. At first glance, the data shimmered with potential. The presence of water vapor, the deep shadows of methane, the unexpected call of dimethyl sulfide. But hope is not proof. Imagination is not confirmation. Only numbers could tell the truth. Statistical analysis began, quietly and methodically. Teams of scientists, scattered across continents, subjected the data to grueling examination. Noise reduction algorithms stripped away the interference of cosmic rays and instrumental artifacts. Models of planetary atmospheres were applied and reapplied, each hypothesis tested against the raw numbers. The delicate dance of wavelengths was scrutinized, ensuring that every molecular signature was real, persistent, and not a ghost in the machinery. And then, across spreadsheets and code outputs, across graphs and multi-dimensional probability distributions, the number emerged: 99.7%. The confidence level that the signals observed, especially of dimethyl sulfide, could not be explained by non-biological processes. In statistical terms, this was a 3 sigma result, a degree of certainty so high it defied mere coincidence. A false positive was no longer a feasible explanation. The universe had spoken through probability. In science, 3 sigma confidence marks a boundary between suspicion and belief. It is the moment where doubt begins to crumble, where the weight of evidence presses down so heavily that skepticism must step aside. For K2-1T-B, 99.7% certainty meant that the presence of biological processes was not wishful thinking. It was the most rational, statistically supported conclusion drawn from the data. But this was no careless leap of faith. Behind that simple number stood rigorous cross-validation. Teams employed blind analysis, removing human bias by scrambling data labels during early processing stages. Independent groups used alternative statistical methods: Bayesian inference, maximum likelihood estimation, Markov chain Monte Carlo simulations, all arriving at the same conclusion. Different tools, different analysts, same outcome. The signature of life was imprinted in K2-1T-B's atmosphere, and math refused to ignore it. The journey from raw data to statistical certainty was not quick. Months passed as telescope readings were revisited, as alternative explanations were explored. Could the dimethyl sulfide be an unknown photochemical byproduct? Could methane persist due to exotic geological activity? The models said no. Geological scenarios could not account for the observed concentrations. Atmospheric models predicted that without biological replenishment, these molecules would vanish on short timescales, broken apart by ultraviolet radiation and photodissociation. Yet they endured, their signals unwavering transit after transit. Equally important was the absence of alternative sources. Volcanic emissions, while capable of producing methane, are typically accompanied by sulfur dioxide and other trace gases, none of which appeared in K2-1T-B's atmospheric fingerprint. Abiotic path. Ways for dimethyl sulfide production, explored thoroughly in geochemical simulations, failed to reproduce the observed abundances. Time after time, the balance of probabilities pointed not to lifeless chemistry but to biology. This growing mathematical certainty forced the scientific community to confront an exhilarating yet uncomfortable truth. K2-1T-B was likely alive. Not definitively proven in the strictest sense, science rarely grants absolute declarations, but with a confidence level high enough to reshape the foundation of exoplanet studies. The impact rippled outward. Grant committees, previously cautious about speculative astrobiology, shifted their priorities. Proposals to study Hycean worlds received unprecedented funding. New satellite missions were drafted to validate and expand upon Webb's observations. Planetary models were rewritten with new parameters: hydrogen atmospheres, thick cloud decks, deep global oceans, no longer barriers to life but potential facilitators. The implications extended beyond science into human culture. Media headlines, once reserved for distant black holes or asteroid threats, blazed with stories of K2-1T-B's mathematical proof of life. Philosophers debated the nature of existence in a universe no longer potentially empty. Theologians revisited ancient texts in light of the growing consensus that life was not unique to Earth. Children, gazing up at crimson-hued artist renditions of K2-1T-B, wondered if somewhere beneath those clouds something or someone was wondering about us. Yet amidst the public fascination, the mathematicians remained disciplined. They cautioned against hyperbole, reminding all that probability is not certainty. They spoke of false positives, of the importance of independent verification, of the need for follow-up observations. But even their caution could not suppress the quiet awe in their voices when presenting their findings. The numbers spoke too clearly to be ignored. K2-18b had, through the unbiased, emotionless language of statistics, told humanity a story. It was a story of a world both alien and familiar, of an ocean cradled by hydrogen clouds, of gases exhaled into the sky, not by volcanoes, but by life forms swimming or drifting below. It was a story told not in pictures or direct contact, but in the subtle rhythmic fluctuations of light measured with instruments of glass, gold, and silicon. In the end, the math achieved what generations of astronomers, philosophers, and dreamers had yearned for. It provided evidence beyond reasonable doubt. It transformed a point of light into a living world. It expanded humanity's cosmic perspective, not by grand gestures, but by the quiet authority of numbers lining up, of probabilities converging, of hypotheses surviving the crucible of rigorous testing. And in that revelation, humanity learned something profound about itself, that our greatest explorations were not of distance, but of understanding. That through the abstraction of mathematics, we could extend our senses across light years, hear the breath of distant oceans, and touch the invisible. K2-18b spoke to us, not with radio signals, not with flashing beacons, but with the enduring, reliable whisper of molecular math. It told us, with 99.7% certainty, that life's reach was longer than we had dared to believe. In the silent corridors of observatories, in the pages of peer-reviewed journals, in the excited lectures of professors, the message echoed. Life was out there, measurable, detectable, undeniable, and it had been the cold, clear precision of mathematics that heard it first. For centuries, humans have pointed instruments skyward, searching for a sign, a whisper, a trace that life exists beyond our fragile world. Yet now, as the golden mirrors of the James Webb Space Telescope captured the atmospheric breath of K2-18b, a new and unsettling question began to take root, not whether we had discovered life, but whether life had already discovered us. It is a question older than telescopes, older than science, woven into the myths of countless cultures. Are we being watched? But where ancient minds imagined gods peering down from celestial thrones, modern minds turned to more subtle watchers, civilizations perhaps far older than ours, listening patiently from distant shores. K2-18b, distant though it is, occupies a special place in this unfolding narrative. As we scrutinize its atmospheric composition, tracing the unmistakable footprints of biology, it is only logical to ask, could intelligent beings, if they exist beneath K2-18b's hydrogen skies, be doing the same to us? Is our Earth just another pale dot in someone else's sky? Have our own atmospheric whispers drifted silently into alien instruments? The sobering answer lies in the speed of light and the symmetry of observation. Our radio transmissions, our electromagnetic noise, our pollutants and biosignatures have been leaking into the cosmos for over a century. From K2-18b, perched 120 light-years away, Earth would be seen as it was in the early 20th century, a world of steamships and early aviation, of wireless telegraphy and the first primitive radio broadcasts crackling faintly into the void. To any civilization observing from K2-18b, we are not yet the digital world we know today. Our televisions, satellites, and internet revolutions have yet to grace their instruments. They would see a planet just awakening to technology, a species fumbling at the edges of communication, emitting a gentle, disorganized electromagnetic fog into space. Yet even before radio, Earth's atmosphere bore telltale signs of life. For 2 billion years, our skies have been enriched with oxygen, a reactive gas unlikely to persist without biological replenishment. For thousands of years, we have altered our atmosphere further, burning fossil fuels, releasing chlorofluorocarbons, modifying our planetary fingerprint. Our existence is not silent, it is encoded in the chemistry of our atmosphere, detectable by any civilization with instruments as capable as our own. This symmetry of detection reveals a profound truth. We are no longer invisible. The moment we became capable of observing life on K218b, we accepted the possibility that we ourselves have been observed. The exchange is inevitable. Light travels both ways. Signals flow outward as easily as they are received. But would intelligent life on K218b have reason to look our way? The answer, paradoxically, may lie in our own behaviors. Humans have historically looked first to the brightest stars, the nearest systems, the most Earth-like planets. K218b orbiting a quiet red dwarf may not have been considered prime real estate in their sky, just as we for so long ignored red dwarfs in our search for life. It is only recent discoveries that have shattered this prejudice, revealing that the universe's smallest stars may harbour the largest treasure troves of habitability. If K218b harbours intelligence, it too might have undergone similar scientific awakenings, advancing from nearby bright targets to faint, distant, promising candidates. Their scientists, their philosophers, may have pointed towards Sol, the yellow star softly glimmering in their distant sky, and wondered if life stirred beneath its planetary retinue. And then, inevitably, they would find Earth. Our planet does not blend in with its surroundings. It reflects sunlight with telltale signatures of vegetation known as the red edge, a sharp spectral feature produced by chlorophyll. Seasonal shifts in atmospheric gases betray the breath of life. Polar ice caps expand and retreat. Forest canopies change hues. Fires release plumes into the air. Earth pulses with dynamic, active life, a signal as clear as the one we have now traced in K218b's skies. Could they have noticed? If their telescopic prowess matches ours, the answer is almost certainly yes. Their version of the James Webb telescope, or its technological equivalent, would have captured Earth's atmospheric dance. They would have seen oxygen, water vapor, carbon dioxide, perhaps methane, and the complex interplay of minor gases that scream biological activity. And if their instruments peered into the radio spectrum, they would hear the faint echoes of our first broadcasts, wars, music, political speeches rippling outward at the speed of light. More intriguing still is the concept of reciprocity in the search for life. Humanity has, for decades, directed purposeful radio signals at specific targets, messages encoded with mathematics, with universal scientific principles, with the hopes of reaching unknown ears. The Arecibo message, broadcast in 1974, pointed towards a distant globular cluster. Other messages have been sent sporadically, aimed at nearby exoplanetary systems, yet K218b, until recently, was not among them. Its location in Leo was passed over in favor of systems more closely matching Earth's parameters. Have we been silent toward them, even as they may have been watching us? Or, more provocatively, have they been sending signals of their own, beaming intentional or unintentional communications that we have missed because we were not listening in the right direction or frequency? The SETI, Search for Extraterrestrial Intelligence community, has taken notice. The discovery of strong biosignatures on K218b reorients the map of listening. Targeted listening campaigns have shifted toward the K218 system, calibrating radio dishes to the coordinates of this distant, water-laden world. Large radio arrays sweep the skies above Leo, passing every crackle, every pulse for artificial origins. Thus far, no signals have emerged, no structured beacons, no unmistakable alien code. But the absence of evidence is not evidence of absence. It is possible their civilization, if it exists, chooses not to broadcast, perhaps wary of unknown listeners. It is possible they broadcast in bands or methods beyond our detection. Or perhaps their evolution took an entirely different trajectory, where technology did not follow radio pathways, or where intelligence, if it arose, chose harmony with nature over the pursuit of long-distance communication. And yet, the most haunting possibility remains. They see us, but choose to remain silent. As we peer into their atmosphere, dreaming of first contact, Perhaps beings beneath K2-18b's dense clouds observe Earth with equal curiosity, weighing the wisdom of revealing themselves. Perhaps they catalogue our changes, our rapid industrialization, our technological adolescence, and quietly wait for us to mature or to pass some unknown test of readiness. The idea humbles even the most rational minds. We are no longer explorers standing on the edge of the unknown, but potential participants in a galactic conversation, one whose invitations may already have been extended without our knowledge. For humanity, this realization is transformative. Our planet is a beacon, our atmosphere a declaration, our technological emissions a signature broadcast to any civilization with eyes to see and ears to hear. Earth, in its complexity, has joined the cosmic dialogue, not just as an observer, but as the observed. And with this understanding comes responsibility. We are not anonymous in the universe. We are visible, detectable, perhaps already catalogued in the archives of distant intelligences. The way we shape our world, the way we treat our biosphere, the signals we choose to send or suppress, all may contribute to how we are perceived in the galactic neighborhood. B may represent the first clear instance where this reflection becomes tangible. As we study them, we must reckon with the probability that we, too, are under observation. As we debate whether to send messages, we must consider how we hear. I've already spoken through our planet's chemistry and radiation. And so, in the quiet hum of telescopes, in the patient gathering of spectral lines, a new chapter of human awareness unfolds. We are part of a larger story, one written across the stars, one in which Earth is not merely a reader of the universe's pages, but a page itself, written in oxygen, in light, in sound. As we look at K2-18b, we must ask not only, is there life out there, but who sees us even now? In the balance between discovery and humility, between exploration and reflection, humanity takes its next step forward, aware, perhaps for the first time, that we have never been as alone as we believed. In all our searching, there has been one enduring feature of the cosmos: silence. A silence so vast, so total, it sometimes felt suffocating. Radio dishes aimed skyward returned nothing but static. Optical searches revealed only the cold twinkling of indifferent stars. And for generations, humanity confronted the possibility that life might be a solitary miracle upon a lonely rock. Yet now, in the spectral fingerprints of K2-18b, in the soft glow filtered through hydrogen clouds, that silence began to sing. Not in shouts or declarations, but in a symphony of molecules, a quiet song of existence pulsing from oceans we could not see. It was not the triumphant contact dreamed of by science fiction. There were no flashing lights in the sky, no majestic alien voices beamed across space. Instead, there was methane, persistent, replenished, water vapor, dense, abundant, dimethyl sulfide, faint but unmistakable. Each molecule was a note, each absorption line a verse, each rhythmic transit across the face of K2-18's red glow, another chorus in a song older and wider than our civilization. And we listened. In this newfound melody, humanity discovered a truth more profound than contact. Life is likely common. Intelligent. Life. Advanced civilizations. These may remain elusive, their lights hidden or their voices muted, but biological life, complex ecosystems, alien biospheres, these seem to weave themselves naturally into the fabric of planets, arising wherever the conditions allow, persisting through time, encoded in the chemistry of worlds. K2-18b was not an anomaly. It was a revelation that silence itself had been misinterpreted. The universe had not been silent. We had been deaf. We had listened only for technology, for artificial signals, for conscious minds reaching outward. We had forgotten the first language of life, the language of molecules, of biology breathing into the air, of photosynthesis tinting clouds, of metabolism etching signatures into the atmosphere. And now, with our golden-eyed telescope hanging in the void, we had begun to hear the true music of the cosmos. It was the music of persistence. K2-18b's song had likely played for millions of years before our species learned to harness fire. before we painted on cave walls, before we named our own planet. And it would likely continue for millions, perhaps billions of years after we were gone, echoing softly beneath hydrogen skies, a constant hum in the quiet theatre of the stars. Yet if life was common, if the universe was alive with unspoken songs, then why the silence from intelligence? This question lingered, heavier than before. Scientists speculated with renewed vigor. Perhaps technological civilizations are brief. Perhaps intelligence is a rare branch on the sprawling tree of life. Or perhaps the technological phase of species is but a transient adolescence, quickly surrendered for more sustainable, less detectable existences. Perhaps we had been listening at the wrong time, or in the wrong way. Or perhaps the universe is speaking, but we have only now developed the ears to hear its gentlest tones. In the breath of K288b's atmosphere, we heard for the first time a harmony we could not deny. It was the harmony of life doing what it has always done, thriving, metabolizing, adapting and enduring. Life that does not build megastructures or beam messages, but life that shapes oceans, colors skies and fills worlds with invisible rhythmic energy. And within this realization, humanity faced a choice. We could continue to search only for reflections of ourselves, civilizations with cities, with machines, with radio waves, and perhaps be disappointed by their rarity. Or we could broaden our understanding, recognize that life's most profound expressions are often quiet, persistent, and deeply biological. K218b taught us humility. It reminded us that intelligence is not the only measure of significance. A world enveloped in hydrogen, bereft of continents, under the dim light of a red star, may pulse with more life than our own. The tapestry of existence is not woven solely by technological threads, but by the innumerable, intricate patterns of biology in all its forms. The silence of K218b was not emptiness, it was balance. It was ecosystems in equilibrium, oceans alive with organisms unseen but unignorable, an atmosphere singing softly across the stars. And in that silence, humanity heard purpose, not only to explore but to protect, not only to seek new worlds, but to safeguard our own. If life bloomed under alien suns, beneath crushing oceans and crimson skies, then Earth's rarity was not in its life, but in its fragility. K218b's endurance cast our planet's vulnerability into sharp relief. Climate instability, atmospheric degradation, ecological collapse. These were not just local concerns, but existential risks to our unique expression of life. Thus, K218b became a mirror, not just reflecting what we might find, but what we might lose. In the quiet that sang from 120 light-years away, we were reminded that discovery was not an end, but a beginning, the discovery of life beyond Earth. So, as an invitation to listen more carefully, to search more deeply, to respect more profoundly the ecosystems both alien and terrestrial. And, in the grand cathedral of the cosmos, Webb's golden mirrors served as humanity's first true organ of hearing, its first sensitive instrument in the symphony of the living universe. We could no longer claim the universe was silent. We could no longer believe life was Earth's exclusive triumph. We stood at the dawn of a new understanding, humbled, awakened, forever changed. As we listened to K218b's rhythmic atmospheric song, as we mapped its hydrogen tides and traced its spectral melodies, we knew this was only the beginning. Countless worlds waited, each with their own songs, each with their own silences ready to be unmasked. The silence had not been silence after all. It had been a lullaby echoing across the void, waiting patiently for ears wise enough, instruments sensitive enough, and hearts open enough to hear. And now we listened. Now, let us drift back from distant oceans, from skies laced in violet haze, from ancient stars pulsing softly in the cradle of Leo. Let the cosmic distances blur, the whispers of molecules fade, and our awareness gently return to the quiet rhythm of breath, to the steady warmth of life beneath our own familiar sky. For though the galaxies turn, though the stars are born and die in silence, here you are safe. Here, in this moment, the mystery of the universe holds you like a lullaby, not asking you to solve it, only to feel it, to rest within it. The weight of distant worlds dissolves, the pull of gravity softens, the wonder remains, but urgency disappears. There is nowhere you must go, nothing you must answer, only the soft drift of thought, the gentle glow of curiosity fading now into peaceful quiet, into warmth, into sleep. Breathe in slow and steady, as ancient as the stars. Breathe out, easy and light, like a ripple upon calm water. In the vastness of space, you are small, but you are also part of the great story. And in this story, tonight, you rest. Tonight, you dream. Tonight, you are at peace.